Hello, I'm Michael Block and I'm working at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany. I'm also a professor at the University of Mainz. GSI runs a large-scale accelerator structure where we can accelerate particles, and one of the things we are known for in the world is making new elements. We have actually been the birthplace of 6 new elements, including, for example, the 110th element that is named Darmstadtium. When the Berlin Wall fell, I was a student at school and I was still studying at that day. When I was a child, I didn't have a clear-cut vision of what I wanted to be when I was growing up, but I always had a strong interest in technical things and in natural sciences. So I'm very grateful that I finally got one of the best jobs I can think of, because I can do new things all the time and I get to use very sophisticated equipment to answer very fundamental questions. And I have always been curious to learn new things. In my research, I try to answer the question, what is the heaviest element that can exist? Many of these very super heavy elements can only be created artificially in a laboratory. They do not exist in nature. They are often very rare and we can only produce one atom in an entire week in some of the most exotic cases. Many of the atoms that we create, or their atomic nuclei, decay in a split second. So we do not have many atoms to study and we do not have much time to get the information that we like to get. Nonetheless, we want to really study their structure in detail and we want to understand why they exist and which chemical properties they, for example, would show if we could make enough of them to create a new chemical compound. In my research, we can trap particles of the heaviest elements in an ion trap, or we can irradiate particles of heavy elements that we have stopped in a gas by laser light. In these measurements, we can get some information about their structure and many of their atomic and chemical properties. For example, we can study their size and shape. Many of the nuclei that we study are actually not spherical, but have a deformed structure and may look, for example, like an American football. According to theoretical models, there are even sophisticated cases where our nuclei may have a bubble-like structure, and we can find hints of this structure imprinted on the absorption spectrum of our light by the atom. In my research, I try to understand the building blocks of matter on the level of atoms and atomic nuclei. Of course, in that sense, my research is of a very fundamental nature and is not aimed to have a direct application, which is partly due to the fact that we can only produce so very few atoms at the moment of these exotic nuclei. However, as in many cases, an application may emerge in the future that we have not even thought of. For example, when the element 95, americium, was discovered in the mid-1940s, nobody would have ever expected that this radioactive element would at some point find its way into smoke detectors. We have still not the final answer what the heaviest element will be. We also do not know what is the longest lifetime that we will find in one of these artificially made heavy elements. One of the things that can keep me awake is the question how to make our method even more applicable to the most exotic and rarest elements. This includes, for example, how can we make the setup more efficient and more sensitive. My family actually thinks that my research is exciting and fascinating. They are intrigued by the possibility that we can make little ions go in a circle